Okay.
Empezó.
Sí. So, hello everyone. In our another Friday meeting of our astroparticle group. Today we're gonna have two talks. The first talk will be given by Andrés Olmos y Aguna. Y Almost Aguna. So the first talk, Yaguna-san is going to give to us. He's going to talk about light dark matter and strategies to detect this light dark matter with anti-ferromagnets. So I will hand over to you. And I need to share yours first of all. Okay. So is this here, right?
No, no.
This
one.
The end.
The end.
Okay.
Yes. Thank you very much for coming here.
Just a minute. Okay. Too much slide. Okay. Well.
Se quebra o no?
Okay. Okay. No more spoilers. Need to accept people in the meeting.
Yes, I will accept that, and let's start with this. Okay, wait a minute. I will receive somebody here. So, okay. Hello, everybody. My name is Andrés, like Mateus mentioned. And today I'm going to speak about anti-ferromagnets and light dark matter detection. So, for one of the different models that we have for dark matter, we need to find new ways to detect this kind of dark matter. So my presentation is divided in 4 parts. First, I'm gonna give a little context that all the people in the group will know, like the evidence and the evidence of dark matter in the universe. Later on, I'm gonna speak about one specific model. I'm gonna mention the way to detect that specific model. After this, I'm gonna speak about the effective field theory that the people in the article was working, and after all, I'm gonna talk about the event rates in order to study this to study this light dark matter. So the context is the next. We have these rotational curves and the gravitational lensing, which one moment, we are having technical issues here.
It's the wire. It's dark matter. No one can see.
It's very dark. So we have the evidence. So some of the most famous one are the rotational speed of curves and also the gravitational lensing. Those are those are some observations that we have to prove that there must be dark matter in the universe. So this is an important component in our universe, which is about the 5%. Today we have most of the universe have dark energy and 5% of dark matter, and later on a little bit about baryonic matter and radiation. We are interested in a study of this 5%, and for this 5%, we have different models. We have the WINS, which is the most popular one. Is highly studied by a lot of experiments, as you can see in the plot. And we have here the famous plot, which is the cross section of the WIN in interaction with the nucleon. But this is not the only model. This is the most popular one, but we also have the interaction massive particles, light dark matter, which is dark matter which has a masses of KV and GV, primordial black holes, and etc. But today I'm gonna speak about the specific one, the light dark matter. with light dark matter, we have another one difficulty, some sort of difficulties. The main one is that we cannot analyze merely the record of the nucleus. We do an interaction between dark matter particle and a nucleus. This doesn't work. This is only valid for masses around GeV, and the light dark matter must be about keV and GeV. So we need to study new ways. And where we can get this light dark matter. So the new strategies is working with low energy thresholds, and this can be attained using some detectors made from which are constructed by semiconductors, superconductors, lower dimensional materials, and etc. But also today, I'm going to speak about the anti-ferromagnet, which is promising. We have some promising materials we are going to be mentioning almost in the end, but that's it. So the new detectors probably we're going to have supermaterial some semiconductors, superconductors, and etc. So the way to detect the light dark matter using anti-ferromagnets or different materials is now analyzing the spin-dependent interaction between a dark matter particle chi and the spins that are in the target. This interaction gives us a magnon, which is a excitation of the spins that are in the target, and this can happen only for a dark matter particle with this mass around the keV. So this is the new way to detect. We can use also ferromagnets, but in that case they study phonons. In this case, the antiferromagnets, we are going to study magnons. So I want to speak a little bit about ferromagnet and antiferromagnet. We have some difference. For example, for the ferromagnet, we have a non-zero magnetization in the ground state. And in the case of the antiferromagnet, we have a zero magnetization in the ground state. Later, I will show a little bit about that. But the emission of a magnon in the ferromagnet and in the antiferromagnet is different. So we have this energy for the ferromagnet, and we have this magnon energy for the ferromagnet, which is going to be quadratic with the momentum, and the maximum energy will give you by this, where I'm going to study the people study the kinetic energy, the dark matter kinetic energy, and the relation between the masses, where this mass corresponds to a magnon. But in the case,
the theta is the magnon.
Yes, magnon field. And later on, for antiferromagnet, we have the emission of magnon, which has a linear relation with the momentum, and we have the velocity of the magnon. And the maximum kinetic energy and the maximum energy that can reach one magnon. This is one of the main differences. We can analyze only one magnon for antiferromagnets. Instead, but in ferromagnets, is something more continuous. But for antiferromagnet, is more discrete. And we studied the excitation of one magnon, and this Y is the ratio between the magnon velocity and the dark matter particle. And for some materials, we have something very surprising, that the velocity of the magnon is pretty similar, is almost equal to the velocity of the dark matter particle, which means that the magnon can absorb all the kinetic energy coming from that dark matter particle. So in order to study this, we have to use an effective field theory. I don't know so much about this, but I'm gonna try to. Yes. Yes.
There's an advantage in use the antiferromagnet instead of the ferromagnet.
Yes, because we are gonna have gapless magnons. So when it's just more is the advantage, where it's more easy to find magnons in antiferromagnets than
the ferromagnets.
Yes. Because in ferromagnets you usually study phonons, but phonon is another thing. In this case, for antiferromagnets, since we are analyzing spin-dependent interactions, it's more easily for antiferromagnets that emit one magnon, for example. So, for magnons alone, I will do it. I will do that in this one right now, actually. So, for magnets alone, we have this. This is an schematic representation of an antiferromagnet. So we have that all the spins are anti-aligned in the antiferromagnetic, giving us a zero magnetization, zero macroscopic magnetization in the ground state. So what we want to study is what we want to study is the fluctuations is the fluctuation in the magnets due to the dark matter particle and the magnets that are that appears after the interaction. We have the particularity, something very particular that will be pre-analogous to ghost-hole bosons. The magnets are right, so it can be taken very similar, not the same, but something pretty similar to ghost-hole bosons. And the fluctuation that we are going to analyze are being around this equilibrium value, where I have this magnetic field and the spin. This is in one direction. Studying for only one magnon, I have the next Lagrangian in the non-relativistic case, where I can describe this Lagrangian in terms of magnon field, the derivatives with respect to time, and this, and for the coordinates. Spatial. And then we have these constants that depends on the antiferromagnet that we are working for. Or going to be
a kind of a Taylor extension.
Yes.
The first equation to the second equation.
Yes.
They put this spin, the exponential, and then they expand in Taylor expansion and get the second equation.
Yes. So, and something that I mentioned is this only for one magnon, but for two magnons, it's gonna be something analogous to a particle and antiparticle case in the relativistic case. Now, coming back to this slide where I made a comparison between ferromagnet and antiferromagnet, is that the dark matter particle, light dark matter, couples when the light dark matter is coupled to antiferromagnet, allows the emission of more than one magnon in each event. So we can have more magnons in each event. So we can this more easily in the case for the ferromagnets. So the central role in this case will be the spin density, which is given by this expression, and will be the observable. So we can obtain by this constant, like I said, is dependent on the part of the antiferromagnetic material, but the observable will be the spin density, and this will be the connection with the dark matter when we do the interaction of the dark matter, as we can see in a moment. So when I speaking about dark matter magnon interaction, I have I can consider some Lagrangian, some models that were considered in the ferromagnetic case, where I have these vector mediators, and where I have the magnetic dipole and cell mediated models, and where I have these vector mediators. And this works only if the dark matter is a composite particle that interacts with standard model particles using a vector mediator as the dark phonon, for example. And we can do an integration with we can do some integration between those models to find the Lagrangian for the interaction between dark matter and magnon will be proportional to the spin density. So this is the reason why we study this is why we say that the dark matter interacts with magnons via the spin density this will give us the sign of this will give us the sign of the dark matter particle of the light dark matter. And this, well,
just which is the dark matter? The Lagrangians, what's the dark matter field?
The Chi's.
The Chi's.
Chi's as the dark matter fields.
Okay. Oh, okay.
Yes, and this is the electron field and so on. So that's somebody want to. Somebody in the call are speaking. Want to speak?
I think someone left their microphone open.
Yeah, probably.
Ask them to.
Yes, can please turn off the microphone. Maybe I can do in that. Okay, thank you. And then with this Lagrangian for the interaction, this Lagrangian for the iteration of the dark matter magnon, we can construct the event rates, this quantity. So we have this integral, and this will be dependent of the material density and dark matter velocity distribution. Well, we know that this pretty similar to mass quantum distribution, and this emission rate of a magnon can be obtained using the Feynman rules that can be derived by using the Lagrangian what we had in the last slide. And this has some particularity that the velocity of the dark matter, but for some materials, like I say, the velocity of the dark matter will be pretty similar. Will be pretty similar to velocity of the magnon. Well, maybe the velocity of the magnon that is emitted after the interaction will be pretty similar to the dark matter particle. But now another quantity that we want to know is the cross section for this. This is the most important because we are analyzing the interaction between dark matter and the spins of the dark matter and the spins of that are in the antiferromagnetic material. So we have the cross section, in this case for mean cross section, and we have for different models. We have for the magnetic dipole and the pseudo-mediated, which will be in function of this mass of the dark matter, and we are going to have a reference momentum given by this that appears in the pseudo-mediated. So in this, we can have some curves, some confidence level curves for the different models for magnetic dipole and pseudo-mediated. Will be the same. This for the 90%, 95% confidence level, and this from different materials. So we have the nickel oxide, which is, for example, one of the materials that that the magnons that is emitted has a velocity pretty similar to the dark matter particle. And we have also the magnetic oxide, and I don't remember the name of this one. And for this range of masses, we're going to have gapless magnon. Later on, for the magnons from this range of mass, for higher range of mass, I'm going to have a momentum larger than the lambda cutoff that Gabi will speak later on. and here we have a more contribution of those gapless magnons, but what we want to study are the gapless magnon. And something that I want to mention that the cross section here that we see is pretty similar to the ones that we have for the winds, only for the lower masses, only this in the range of the keV. This is I showed the effective field theory and all that thing for only one magnon, but for two magnons will be pretty much the same. In the article, they mentioned that will be the same. Actually, the plot will be the same if we study two magnons and so on. This is for the magnetic dipole, and for pseudo-mediated, we'll say we have that here for higher masses. The behavior will be different. Here, this part will be increasing. This is for the free materials that I mentioned. All of them are antiferromagnetic, and that's all. That's all. This is since for those values of keV, we can obtain a cross section pretty similar to the WIMPs. And at 95%, the antiferromagnetic materials shown here are pretty promising in order to find the light dark matter particle. I may probably more new detectors, probably for direct detection, gonna be about I'm gonna use those antiferromagnetic materials and other materials like semiconductors and so on. That's all. Thank you.
Question. In the previous slide, that omega is the appointment, so
This is the amount of just this for the light dark matter.
okay, so the light dark matter is 5% of the total dark matter.
This
This is an assumption, or
is an assumption.
Okay.
So thank you.
Okay.
yes, we can hear.
Yes, I can hear. We are considering what?
Two-dimensional.
Two-dimensional? Yes. I don't know. I don't know about that. I just they study some kind of precession on the spins in the materials, but I don't, maybe that adds some degrees of freedom, probably. That's a good question. That I question them too. I don't know. There's the only way to works. This is only works if we consider dark matter particle as a composite particle. That's the way. Probably we have some change, but I don't know clearly what could have changed in that case. What? Probably we have to be a really low temperature because there's a low energy threshold, and like I said, some detectors will be semiconductors, superconductors. They need a requirement to be to have less temperature in order to get lower energy threshold. So probably gonna be cryogenic or something like that. Yes, I will. I can send. I can send it.
Any more questions? No? So let's thank the speaker again.
Thank you.
So thank you so much. Let me see if there's some questions here in the chat. Okay, no more questions. So I am going to end the live and start another one. So thank you